안녕하세요. 지금부터 2023학년도 과학 분야 노벨상 수상자 초청 특강을 진행하도록 하겠습니다. 오늘 사회를 맡은 인천과학예술영재학교 교사 김예언입니다. 참고로 오늘 특강은 인천시 교육청 유튜브 채널을 통해서도 라이브 방송으로 진행되고 있습니다. 특강 진행에 앞서 학생들이 준비한 작은 연주회를 진행하도록 하겠습니다. 피아노 독주와 피아노 트리오 연주가 준비되어 있습니다. 먼저 피아노 독주는 존 슈미트의 All of Me를 2학년 유성진 학생이 연주하도록 하겠습니다. 멋진 연주 감사합니다. 다음은 피아노 트리오 연주입니다. 포르 우나 카베사의 여인의 향기 OST를 1학년 한수연, 윤준혁, 서인성 학생이 연주하겠습니다. 네, 감사합니다. 저희 학교 이름처럼 과학과 예술은 함께 있을 때 시너지 효과가 난다는 생각이 듭니다. 네, 다음은 인천과학예술영재학교 심현보 교장 선생님의 인사 말씀이 있겠습니다.
Good afternoon and welcome. I am Hyunbo Sim, the principal of Incheon Academy of Science and Arts. I believe today is the most meaningful day since the establishment of our school. I would like to welcome all the students, teachers, and parents who have joined us here today. I also extend a warm welcome to those who are watching the lecture through YouTube due to a limited sharing. I would like to express my gratitude to the staff of the Nobel Prize organization in Sweden, including the direct cast for taking this honorable opportunity to be with us here today. Our school is a place where talented young people with outstanding potential nature their dream and demonstrate their abilities. We are always in pursuit of knowledge, experience, and a unique idea. In particular, I believe that today audience consists of some of the most passionate and skilled students in mathematics and science in South Korea. Today, we have prepared a special lecture that will further illuminate your goals. Thank you to Professor Michael Levitt, and all of you for speaking today. Thank you.
감사합니다. 다음은 노벨재단 수석 파트너 관계 관리자이신 레티시아 드 샤온님의 인사 말씀이 있겠습니다. The following is a greeting from Leticia de Chao, who is the Senior Partner Relations Manager at the Nobel Prize Organization.
Hello, everyone. Thank you so much, Professor Shim Hyun-bo, for hosting this wonderful lecture at the Incheon Academy of Science and Arts today. So I am here in Seoul as a representative of Nobel Prize Outreach, and our goal is to inspire dialogue on the most pressing challenges through the voices and stories of Nobel Prize laureates. As part of our activities, we organized yesterday a large conference on the topic Future Learning, Exploring Science and Technology, and I think that some of you did participate. Actually, what strikes me when looking at your curriculum is how the Incheon Academy of Science and Arts is blending arts, humanities, and science to inspire creativity, to foster innovation, to support talent and intelligence in its various forms. And is that not what the Nobel Prize is about as well? It's about awarding cross-boundary knowledge and benefit from different perspectives to solve our challenges: literature, peace, physiology and medicine, chemistry, physics, and economy. So on that note, we are very pleased to welcome today Professor Michael Levitt, who will take us through an exciting journey on the impact of biological intelligence, human intelligence, and machine intelligence on innovation in science and technology. Professor Michael Levitt has been awarded the Nobel Prize in Chemistry in 2013, so it's a 10-year anniversary now, for the development of multi-scale models for complex chemical systems. So we will have a 1-hour lecture followed by 15 minutes to allow you to ask any question you may have to Professor Levitt. So enjoy this opportunity. And I would also like to thank our Nobel International partners supporting all our outreach activities, and that's 3M, ABB, Capgemini, EQT, H2 Green Steel, and Scania. So please, Professor Michael Levitt, welcome on stage, and the floor is all yours.
It is actually very exciting for me to be here. I have spoken at many universities, many conferences, even quite a few schools. But I think today I'm speaking at one of the very best schools in the world. I think you all need to realize how fortunate you are, but also not to feel too much pressure, because life is full of surprises, and we need to live life without planning too much. So to start my talk, wrong way. Oh, sorry. So the title is about the impact of 3 intelligences. We all know about human intelligence. The school is about human intelligence. Everybody has heard too much even about machine intelligence, AI. But in some ways, the most important intelligence is biological intelligence. There should be a time here, right? I don't see a time. Just so I know what the time is, I don't... Let me know towards the end, because I can speak for 5 hours. Okay. So essentially, we have in this world three intelligences: human, machine, and the biggest intelligence on Earth is biological intelligence. Because everything we see that is alive was made by biology. So biology is much smarter than humans because biology can make humans. In the same way, we are probably smarter than machines because we can make machines. So biological intelligence, this works, good. One of the most important lessons of biology comes from evolution. Biology started from nothing maybe 3 billion years ago and has led to all the life on Earth, from leaves to fishes to birds to human beings to animals to everything. And essentially, in the tree of life, the mouse is unreliable, so I won't try to use it. In the bottom corner, we see the beginning of life. Very, very simple life. Essentially, bacteria and another life form called archaea. But let's just think about bacteria. And then we have complex life, and life has become more and more complex with evolution. That isn't obvious why that should be, but this is what we see. So essentially, there are two kinds of evolution in our world. There are bacteria, which in bacteria, the man bacteria gives his genes to all his children. The children are almost an exact copy of the genes of the parents. Bacteria started out about 3 billion years ago, and bacteria today are still very common. We cannot ever see them because they're very small, single cells. But for example, in our body, we have about 1 kilo of bacteria helping us with our food. We probably have more bacteria than we have cells in our body. So in bacteria, we have survival of the fittest. The best bacteria gives his children his genes, and if that is successful, there will be more of that bacteria. But higher organisms that we call eukaryotes are different. They always have a mother cell and a father cell, and the children are a mixture of the mother and the father. The children are a random mixture, half the genes from the mother, half the genes from the father. Biology, if it wanted to, could give the children the best genes from the mother and the best genes from the father, but it chooses not to do that. So really, we have to ask, what does evolution teach us? Is it survival of the fittest or survival of the most diverse? And when we go back and look at the tree of life, we see that the bacteria shown here are a very tiny part of the diversity of life. Life became very diverse and very complicated as soon as we had a male cell and a female cell mixing. So it was this that led to an enormous change in life. Also, as organisms became more and more advanced, they also became more and more complex, many more cells. The simplest eukaryotes are things like yeast. Yeast have just one cell, a male cell and a female cell. Human beings have about 250 different cells. They also have a brain. And this evolution of intelligence is because if you are more complicated, you are more diverse. So why is diversity so important? And the reason is that nobody knows about the future. None of us here know what the future will bring us. There could be some change in the world 3 days from now, and only the people who cannot use a phone will survive. Maybe the homeless will survive. It could be the other way around. So we want to have one species, human beings, that are as different as possible from each other. So men are different from women, not better, not worse, And each of us have different genes, and this is very, very important for the survival of the human race, this diversity. So really, it is the survival of the most diverse. Biology is also very, very clever. It essentially invented how to create life. And as you will see, life is really remarkable. It invented the DNA, it invented proteins, it invented the machine that converts the information in DNA to the information in proteins, the ribosome. It invented cells and nerve cells and hands and eyes and brains. It did all this without anyone having greater intelligence. Everything came from inside. It was not like you make something in a laboratory where you come from outside and you make it. In life, everything starts. An egg and a sperm lead to a whole human being by a process of self-assembly. So it is really miraculous. Now, a little bit about human intelligence. So one of the very important things about human intelligence is that we always learn from people who lived before. We learn through what they write, through what videos they made, through their ideas, through the music that they composed, but we also learn very much from mentors in our life, great teachers, a parent, and so on. Mentors are very important. And in many ways, scientists, great scientists, can also be great role models. And I myself, when I was quite young, maybe 20 years old, came into contact with many great scientists who were great mentors to me, and I remember their lessons until today. My great scientists actually came from a small laboratory in Cambridge, England. This is the building. It's a small building, maybe 200 people. But you will see that from this building, which started maybe in 1965, they ended up creating amazing discoveries. And these are some of the people who influenced me very much. The first is a man called Max Perutz. He is the man who invented protein crystallography, the method that allows us to see the structure of protein molecules. He's also the man who was the leader of this laboratory. Max Perutz had working for him another man, John Kendrew, and John Kendrew used Perutz's method to solve the structure of the first protein. Protein structure is very complicated. 1,000 atoms, maybe 100,000 atoms, and all the atoms are in a very precise position. So the architecture of a protein is much more complicated to understand than the architecture of a building. There are no straight lines. And here is the structure of myoglobin. Back in the early days, most magazines did not publish in color. Scientific American was a science magazine, still is a science magazine, but it published in color. And here you can see a structure from Kendrew. There was no computer graphics in those days. It was painted by an artist called Urban Geis. And this picture is on the cover of Scientific American, which is in color. So for this reason, great science was often published first in Scientific American and maybe later in Nature or Science. This was wonderful because this magazine was read by many 12-year-old and 13-year-old and 15-year-old children. There was no internet back then, but this magazine had a very important role in disseminating knowledge. So Kendrew worked for Perutz. This person everyone will know, Francis Crick, the person who discovered the structure of DNA together with Jim Watson. The structure of DNA has two chains, and these chains encode the information that we have in our lives. I'm sure that most of you know that. What you don't know, which I think is in some ways also very interesting, is that when Crick did his work on DNA, he was actually the PhD student of Max Perutz. And Max Perutz was very helpful to their work because this photograph up in the top right corner is an X-ray picture that was taken by Rosalind Franklin, another scientist, And Perutz had seen the picture and showed the picture to Crick and Watson. Scientists help each other like that. But what is really interesting is that in the famous paper that Crick wrote in 1953, The Structure of DNA, in Nature magazine, Perutz's name isn't there. It's not Watson, Crick, Perutz. It's just Watson, Crick. They don't even thank Perutz. So this is an amazing example of a senior scientist wanting to give young scientists independence and responsibility. And this, I think, is one of the most amazing examples, because this is probably one of the most famous papers that has ever been written. But the person, the leader of the lab, the boss, the PhD supervisor, did not put his name on the paper. It would never happen today. So these heroes of mine actually used physics and chemistry to reveal the sequence of life. You know, we often talk about areas of science, Nobel Prize for chemistry, Nobel Prize for physics, and so on. But in real science, everything is mixed up. I got a Nobel Prize for chemistry. It's the one subject I've never studied. I have never studied chemistry. I have studied physics, mathematics. I love computers, and I work in biology and medicine. So the average of all of that is chemistry. And the secret of life can be put onto one slide. We have the structure of DNA, which is keeping the information of life. It is like the library, like the internet, all the information is there. But information is just a code. Information is in one direction, one dimension. In order to interact with the real world, which is three-dimensional, we need shapes. And the shapes are made by proteins, and the proteins have a function. The proteins do something. So in this example, the protein is binding to a food molecule and maybe converting it into energy. Now, cells with that protein will do better. There will be more copies, so this DNA will increase in copies. And this is the secret of all of basic life. So DNA is a very pretty structure, modeled by Crick and Watson. There are two chains. You can see a green chain and a red chain. The two chains are important because if there's an error in one side, the other side will correct the error. And it's very important that the library not become corrupted. DNA is a code. There are actually 4 different kinds of groups. It's not a binary code. It's probably a quaternary code. Each position is 2 bits, not 1 bit. And this is the code. And in our bodies, we have code that is about the length of a meter and has about 3 billion letters in it. So it's a big letter. But 3 billion letters is not so much. Okay. Now, what does the DNA do? The DNA leads to a protein chain, the chain here. And the protein chain, I'm trying to work out how the pointer works, but I can't get it to work, actually has 20 kinds of amino acids, so the protein chain is more pretty. And you can see in the DNA, it's quite hard to see the difference. The difference is very small, 1 or 2 atoms. But the protein I don't know how to advance the slide. Okay. The protein, you can see, has different shapes, and the different colors are for different shapes. And the colors repeat, but there are 20 different colors, so the DNA codes for the protein chain. But the protein isn't long and thin. It's collapsed into that small shape for that long shape. And the collapsed shape is strongly three-dimensional. But that shape is not random. In our bodies, we have that protein, every one of us. And the protein has exactly the same shape. And that shape is about maybe 2 nanometers across. And that is tiny. Even in the very best phones in the world, the printed circuits, the line thickness is 5 nanometers. So nature can make a machine that is 100 times smaller than the best chip making in the world. And this machine acts because of its shape. It fits into other shapes. So essentially, life is a bit like clockwork or a puzzle. You make these shapes They interact, they build skin, they build brains, and so on. And in our body, we have about maybe 30,000 different protein shapes. These are like the words of the DNA language. And this gives rise to all our intelligence, to all our lives. Now, it turns out that Nobel Prizes are not won evenly. On average, I think in the world right now, it's about one Nobel Prize for, I think, something like 40 million people on average. But some places have more Nobel Prizes, and it's interesting to ask why. What are they doing that makes it special? Now, there are a few places, but I'm going to take the one that I know best because I was a PhD student there, and also it is done very well. So the same laboratory in Cambridge, the Laboratory of Molecular Biology, it actually has won 28 Nobel Prizes since 1958. So in something like 60, 65 years, 28 Nobel Prizes. That's a big number. Japan has won, as a whole country, 28 Nobel Prizes. And here you have a laboratory with space maybe for 300 people, and in 60 years, maybe 3,000 people have been there, and 28 have Nobel Prizes. What is the magic? So it's interesting to ask, and people have had Nobel Prizes who are faculty members, who have worked at that place, but also many people came as visitors and got the idea for their Nobel Prize winning work as postdoctoral fellows or visiting scientists. So I tried to understand what is the recipe, what is the rule that the Medical Research Council Laboratory of Molecular Biology uses. So the first rule is what Max Perutz did to Francis Crick. Make young scientists independent and responsible. I remember being a student there, maybe aged 21 or 22, and an important Nobel laureate is invited to go and give a special lecture. He doesn't feel like going, he sends me. I mean, can you imagine, beginning of your PhD, somebody says, okay, will you please go to the Royal Society and give my lecture for me? Terrifying, but you learn from that, and this was very common. Second thing is, the groups are quite small. It isn't like Max Perutz has 20 people who work for him. He has 3 or 4, maybe 5. Some people are working by themselves. It is a hierarchy where you have many people together, all equal. But they get lots of support. The grant support is quite high, maybe here in today's money, $1.5 million per group per year, and they don't have to ask for money. They don't have to ask for grants. The leaders ask for the money, and the young people don't worry about money. They just do their science. Almost no bureaucracy. If I was there now and I wanted a new iPhone, I would go to stores and I would say, I want a new iPhone. They would say, just sign and give me a phone. Maybe ask me what color I want. Same thing for chemicals, expensive chemicals. Researchers just go there and sign. The pressure on people is very high because you are as good as your next paper. No one cares that you have a Nobel Prize, that you did this. What are you doing now? What is your next paper? And that's very difficult and very important. And very little hierarchy. I remember at tea time, you would sit next to Nobel laureates and speak to them as normal people. And that is also a very good lesson. So let me just say something about my work. And I might cut this short. But so my work was in... forgive me. Okay, wonderful. So my work was in computational biology. And I was very lucky because I grew up at a time when biology was just beginning, but computers were also beginning. And sometimes I feel that I was like somebody in a boat pushed by 2 big rivers, the river of computing, the river of improvements in biology. And I actually myself loved computers. I was very impressed by computers. Now, computers in 1965, 66 were really weak. They could do nothing. You know, maybe all the computers in the world then were 1/100th of an iPhone, very weak. Okay, so I actually have a paper in 1969 in Nature, and it's interesting because Crick's paper was in Nature, and Perut sent it and didn't put his name on it. And this was work that I actually did with Crick to make a model of an RNA called transfer RNA. And he said, just work on it freely, and I will send it to Nature for you. And he sent it to Nature, and it was actually published in 22 days. Now, this is before there is internet. The proofs came back as teletype. Very early days. No photocopies. Very, very early days at that time. John Kendrew actually sent me to go and work in Israel before my PhD. They would only accept me in Cambridge if I went to Israel before. I didn't want to go to Israel. I wanted to go to Tokyo. I wanted to go to Boston, maybe Paris. I had lots of good ideas. He said, you know, you go to Israel. And he wanted me to go to Israel because of this scientist, the older scientist here, and that's how I looked back in those days, Shneur Lifson, and this is 1968, 69, to try to, this man, John Kendrew, realized that we wanted to understand protein structure, and that proteins were just lots of small molecules connected together. And Lifson was working with Varshil on the structure of small molecules and how you can use computers to calculate the structure of small molecules. So I went there and was able to, in my year there, do some important work, and then go back to Cambridge to start my PhD. But I already had almost finished my PhD, so I was able to then work on this problem because it was fine. Anyway, I came back to Israel and worked again with Aryeh Varshil, who shared the prize with me. And this was a very early paper in protein folding, trying to understand how the long chain in proteins folds up. Great progress in this problem has actually been made in the last few years by computers, who are using lots and lots of human information and bringing it together. Okay. Much of my work was on simulating the basic machinery of life. We've seen the secret of life, but the secret is not stationary molecules, it's moving molecules. So here is an early movie of, I think it's going, but maybe not. Okay, a very early movie made in 1978. This movie was unbelievably expensive. Each frame was $500,000. It was made at the National Institutes of Health by one of the first computers in the world in computer graphics. And the person who had the algorithm for drawing the spheres ended up becoming one of the founders of Pixar, which is a very important animation studio. This is just showing water moving. Water is a very simple molecule. Water is very important because the molecule is very simple, but the behavior is very complicated. And there are many things in all of life where the basic unit is very simple, but the behavior is very complicated. This is showing benzene in water, and in water, benzene comes together. So you will see the benzene molecules sticking together. This is an alpha helix, which is part of a protein, showing that it is stable in the simulation at room temperature. It doesn't come apart. This actually was a structure proposed by Linus Pauling, who was one of the greatest chemists who ever lived, a real chemist. He has 2 Nobel Prizes, one for chemistry and one for peace, because he opposed the American restrictions on science and free thinking. And this is just a picture of DNA. I think it's stopping. It's good, yeah. Okay. So here are some early movies of proteins. This is just showing that we can also simulate how molecules come apart. This is an alpha helix unfolding. I'm going to we'll see, it's a good chance to rest. The structure comes apart, and this is important because real proteins come apart. We'll now see what protein folding can look like, or unfolding. Here I just took one end. This is a very old movie, made in maybe 1980. I took one end of the chain and pulled it in the computer, and then just reversed the frames. Movies are very important because proteins are very complicated, and seeing them gives you a feeling that you cannot get. So the movies are not made for audiences, they're made for the scientists themselves. This just shows a protein folding, trying many shapes, and then folding. It quietens down. This was actually a protein that was solved in Sweden by Anders Liljas. And this is just showing a full protein at high temperature, coming apart. And again, understanding this motion is very important. This just shows some of the sticky groups, the benzene groups holding the molecules together like glue. And you can see the pink ones are more sticky than the blue ones, and the pink ones are in the middle. So all of these movies are fairly old. Don't go. I need my next slide. Okay, and these are more recent movies that show what we call as functional motion. So this protein is the protein called myosin that is in your muscles. And the molecule moves in a very interesting way. Essentially, something chemical happens over here that pushes this top, and in the end, it moves a great deal. And this is the protein that is in your muscles causing motion. But it's not just in human muscles. Anything in life that has motion is using the same protein. Nature is always reusing pieces that work. This is the ribosome, the machine that actually makes the protein from the DNA. And again, this is just showing the motion. It is quite complicated. This is now showing the motion where it reads the DNA and makes the growing chain. And this is a real research result based on hundreds of crystal structures, and something that I'm actually still working on. I started working on it about 5 or 6 years ago, and then for various reasons, personal reasons, I moved on to other things. Can you advance again? Sorry. Okay, so I've been very lucky in my life that what I have done has been very basic fundamental science. But somebody once said, and I forget the name, that it's impossible to do basic science that has no application. And one of the really good examples is that the mathematician Euler in the 18th century found a way to factor very big numbers, number factorization. That sounds useless. But all the world's banking, all the communication that is secure, depends on that fact. So all of coding depends on the difficulty of factorizing large numbers, which is amazing. I mean, if you were to put a value on Euler, if Euler had royalties, he would be the richest person in the universe. He would have, every time you make a message, he would get something. So it's very difficult to do something that's not useful. In my case, I did work that was applied, but it was a long time ago. It was in the 1980s. And I'll just jump one ahead. I was working in basic science on the structure of antibodies. So antibodies are proteins that recognize anything. They recognize viruses, they recognize genes, they recognize DNA. And the way they recognize, it's like one hand and another hand come together, and they have 6 fingers, like this. And the fingers can make different shapes. And depending on the shape, which is fixed, they can recognize different things. So there my fingers are recognizing an apple, but they have other shapes. And in our body, we can recognize hundreds of thousands of different shapes. And when you get immunized, you actually make more of a certain kind of antibody. So antibodies are very important. They are like the soldiers of the body. And antibodies, I was studying antibodies theoretically and came to Stanford in 1987. And Stanford has always been very good at applying science. So people said to me, you must join my startup company. I said, what is a startup company? But I joined a small startup company that was called Protein Design Labs, that was started by a person at Stanford who didn't get a tenure position and a mathematician. And they wanted to make proteins, but then they decided to make antibodies. And this is a paper that was published in 1989. So it says, antibody that binds interleukin-2 receptor. So interleukin-2 receptor is a protein that is sitting on the surface of cancer cells. If you have a protein that binds the cancer cell, you can kill the cancer cell. This is much better than chemotherapy, but it only kills the cancer cell. The trouble is that antibodies are made by taking cells, cancer cells, and injecting them into a mouse or a rabbit. The mouse and rabbit make the antibody, and then you take it out of the mouse, and you can produce it in the lab. The trouble is that human beings do not like mouse antibodies. Human beings like human antibodies, and this is why we have the word here, a humanized antibody. So even back then, it's a computer operation that takes an antibody for a mouse or a rabbit and makes it like an antibody for a human. And this had been first done by a scientist actually in Cambridge, LMB, Greg Winter, who got the Nobel Prize, I think, 3 or 4 years ago. Greg Winter said, what you do is you take the two hands, you take the fingers from the mouse and the hands from the human. But the fingers are not sticking out, they're actually bent back like loops. So what this paper said is, you take the fingers from the mouse, but you also change some amino acids in the human part. That seems like a very small change, but in a patent makes a huge difference. Because if you also make changes in the human part, then you get better antibodies. And in fact, this method was very important in the very first biological drugs. The company Genentech, that later became Roche in Silicon Valley, used this method to make some very important, well-known antibodies. Now, I always tell people, I hope you don't know the name of these drugs, because if you do, you probably have somebody in your family who has cancer, and you don't want to know that. But Herceptin is a drug for breast cancer, and is very, very important, because some breast cancers express the HER2 receptor on their surface, and an antibody against them can cure their cancer. But in fact, Protein Design Lab also made a lot of money. They made probably $1 billion just from their patent. So this gives me the feeling to say that I have done some applied research, but it was probably coincidental. Okay, AI. So AI we all hear about now, but AI is an old subject. When I started my PhD in 1968, I remember going to the library in Cambridge and reading books about AI. AI books were there, but AI was very weak. AI became very important, not because of defense, not because of powerful science, but because of teenage boys. Now, how did teenage boys make AI possible? They like to play video games, and they wanted the video games to be very fast. So when you shoot somebody, they fall quickly. So they had to develop very, very fast computer chips called GPUs, or graphics processing units. And these machines also allow you to do AI calculations very quickly. So it's interesting sometimes that the reason for development is not what you expect. Like in evolution, you don't get what you expect. Okay, so what is the basic idea of artificial intelligence? It is very, very simple. Here is a model of a nerve cell that actually goes back to 1943. And this is the model of the nerve cell that is used in AI. You have on the left, my left, dendrites, sorry, on your left, dendrites, and these receive signals from other cells. The signals go to the cell body, the signals are weighted and added up, and then the total signal is sent out along the axon to other cells. So now these axons connect to dendrites. So this is a very simple unit. You can write it mathematically as the input is multiplied by a weight, a number is added to it, and you get an answer which is then added up with some kind of bias to it. So it's very simple. A little bit like the water molecule is very simple, H2O, but it leads to very complicated behavior. If you take many of these and put them together, you actually get intelligence. Just to let you know, in ChatGPT, there is something like 500 billion of those altogether. And the calculations are very fast because of the GPU used by children's games. They put them together by having one connect to the next, connect to the next in a network. The network learns by changing the thickness of the lines. And when the network has learned something, it looks like this. But this is a network with 24 units, but in large language models, there are billions of units. So they're large. Okay. Now, one of the very most interesting things about AI is how the machines learn. So normally when you learn, there's a student who doesn't know something and the teacher who knows everything. But this is fine when you are learning something that you know. If you want to learn something that nobody knows, for example, how do you draw a picture of a dog? What are the rules to draw a picture of a dog? It's very difficult to say, you first draw the eyes. It won't work. So here we have a thing where we have two students. One is called a generator. He makes pictures. And the other is called a discriminator. He tells you, is the picture real or fake? So it's a little bit like you try to trick the discriminator by giving him something that's fake. And the discriminator tries to say, no, 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 that's wrong. And each time the generator says, here I give you a fake, and the discriminator doesn't see it's a fake, the generator gets a point. And each time the discriminator says, no, 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 I see the fake, the discriminator gets a point. As a result of this game, the generator becomes better and better at making pictures of dogs. And the discriminator becomes better and better at discriminating fake pictures of dogs. And in the end, both sides know how to do something. The generator can make good pictures of dogs, and the discriminator can tell a good dog from a bad dog. So this is very important. This method is used for language, for proteins, for anything. This is the basic idea. And actually, I think in the future we will find a way to use generative and reversal networks for learning. I made a mistake there. It should be generative, not general. So basically, this is a way of teaching which is interesting. And another good thing about this is that when you have a teacher and a student, and the teacher knows very much, the teacher doesn't even understand the problems that the student has. Here, both start low and both come up. So I'm not sure what's going to happen. Okay. So artificial intelligence today, for me, the entire world changed on the 30th of November last year when ChatGPT 3.5 was released to the public. And I myself have been using it all the time. A few hours ago, I asked ChatGPT, how do we fix the traffic problem in Seoul? And he gave me 3 pages, which all seem very sensible. You can ask ChatGPT anything. I've had an argument with my friend, how do I fix the argument? I argued with my wife, how do I fix the argument? Anything you want. Where do I find the most spicy food in Seoul? Knows. It's amazing for anything. So basically, on that date of release, we had GPT 3.5. There was a better version. Version 4 came out about 3.5 months later. The better version costs money, and it's not actually so easy to access. Some countries you cannot even access it at all. But it's much, much better. The better model is trained on about 1 million books. Maybe it's 10 million books. All the books in the world. In all the languages in the world. So this is a huge amount of information. And the GPT is continually feeding this information into its neural net and is being trained to give good answers, to write good sentences. It's also trained by human beings. Human beings ask it questions early on and give it good points for good answers and bad points for bad answers. So there's a lot of training going on, but even then, it's relatively simple, and it actually has something like 1 trillion optimized parameters. So that means 500 billion neurons, like a human brain, very, very big. So I have been using ChatGPT for 9 months, and I use it all the time. It's on my phone. I use ChatGPT. I also use Google Bard, mostly ChatGPT because I got used to it. So the most important thing I use it for is writing computer programs in Python. I'm sure here you learn Python, but I grew up writing computer programs almost 60 years ago. So I was writing in Fortran and C and C++ and Perl. But I don't know Python. But together with ChatGPT, we can write a Python program in one day. Complicated program, doing very difficult things. It's not just ChatGPT. It's definitely not me, but together. Many, many questions. This doesn't work. Please fix it, and so on. It can even take old programs from 40 years ago and tell me how they work. I have forgotten by now. Wonderful thing. It translates languages amazingly. My slides were written in English and translated to Korean almost entirely by machine. I actually gave the slides to a professor at Konkuk University, and he said there were some errors, and I think you may have errors in the book which have been fixed here, but not many errors. And it's quite difficult to translate because the sentences are very short. There isn't much context. It's good for medical advice. It's good for legal advice. It's remarkable. Each time I think of something strange to ask it, and you get an answer. So it keeps on teaching you, and you keep on getting smarter. I think I'm going to leave this because it's perhaps unimportant, or maybe I'll say something very quickly about it. So basically, I was saying before that many water molecules in a box give rise to the property of water. But we still don't really understand in easy language why water has its properties. We know that many water molecules in a box moving around give us water. And there are many things like that where it's very hard to find a simple explanation. And then I found a paper by a statistician, Galich Morley, that basically said that there's a trade-off. Either you can explain or you can predict. And sometimes good prediction can't be explained. So these large language models, no one really understands why they work. They were such a big surprise because even the developers, until people started to ask them crazy questions, they didn't know they could answer them. So again, we have this problem in AI. Difficulty between deciding whether we want explanation or prediction. And this is very important for education because we like to explain things. We like to understand why the moon goes around the Earth and the planets. But some things are not easily explained. They're still true, but we can't always explain them. So there was a nice review actually in Nature in December 2022, and it was nice because it's before ChatGPT. And they were suggesting ways in which scientific AI could be used in science. And basically, these are some of the things they suggested. Identifying surprises in literature, finding surprising concepts, rather obvious things, but the fact remains that with these things, no one even knows what they can do. Just try and see. And this is one of the things that it's a difficult thing to learn to do. And I tell everybody, play with AI models. Just play. Don't learn them, play with them. Like them. Make them your friends. And don't worry if they don't tell you the truth all the time, because your friends don't tell you the truth all the time. People tell you things that are mistakes. You have to learn to live with mistakes. Very important. So my summary is that we have these three intelligences. These pictures were actually made by Midjourney, so they're more fancy. The very first picture, though, came from the art district of Beijing, Shaochuandi. This is a school of science and art, and my wife and I are like a couple of science and art. She is a real curator of Chinese modern contemporary photography and Israeli contemporary photography, and she is organizing exhibitions all the time, so I am meeting artists all the time. And I see lots of parallels between art and science. In fact, in Beijing, there's a very good art school called CAFA, the Central Academy of Fine Arts. And my wife and I actually gave a lecture there about science and art. But I probably didn't see enough that this was an art place. I might have had a more art lecture. Okay, so I got to the end of my lecture, and here's a summary. It's an important summary. So 3 billion years ago, we had man, a male bacteria who made a copy of himself. And then about 1 billion years ago, nature invented male and female. So we had man and woman. Man was very good, he was simple, the fittest survive. It was hard world out there. But as soon as there was man and woman, complexity survived. The more complex you are, the more you will survive. So actually, instead of just surviving, we were thriving on diversity. All life just blossomed. And I wonder today if we can't think about a three: man, woman, and machine. And this will lead to a hyper-complex paradise, or perhaps a hell. You know, we have a choice. We can embrace AI, use it to make each of us better, or we can have a problem. Now, this was the end of my time. The way I translated my slides is I took all the English text out of my presentation and gave all the English text to ChatGPT and said, please translate this to Korean. And with ChatGPT, a very important lesson to know is sometimes in the middle of giving you an answer, it stops. And you have to say, go on, or continue. If you forget to say that, it won't continue. So we translated 10 slides, and then I said continue, and 20 slides. And actually, I was talking to somebody on the phone, and I just every now and again went to my computer and said, go on, go on. And I didn't realize that it got to slide 99, but there were only 60 slides there. So ChatGPT decided by itself to write things in English and in Korean. And these are some of the things they wrote, and it was actually quite interesting. So, you know, you can read it. It's not my words. It's ChatGPT completely, and that's one. And remember, it's doing this from just reading my titles. It didn't read a paper. It just read my titles. And I didn't ask for it. So, all good things. Sorry, don't want to miss anything it said. Connecting different domains of science. Is it okay?
Yeah, they're skipping it.
Okay. Interaction of AI and biology. I could have mentioned art here, but it's not me talking. It's just the voice of AI. And it goes on, the evolution of AI, mimicking human intelligence. I actually haven't even read this because I feel bad reading words that are not my own. But it was very funny. Limits of technology, human ingenuity versus machine ingenuity, embracing the unknown, value of diversity, the beauty of simplicity, the power of teamwork, courage to take risks, patience in adversity. I chose the ones that there was some that I didn't like, so I left them out. But I like these. Importance of integrity, very important in science and in everything. If you lie, you only lie to yourself, and lying to yourself is a big mistake. And then I stopped saying go on. So basically, just to summarize, I think that we live in an amazing time. I am 76 years old. I witnessed the birth of computers, computational biology, the internet, the smartphone, and now I see this. And for me, this is the greatest one. I have been playing with AI, and I call it playing, maybe wasting my time, because I want to understand it. It's as if a very smart person came from Mars, and we met him. You have to talk a lot to understand. And I think everyone, I tell them, play with AI. It's useful for many things you don't realize. And it can be more useful or less useful. But I myself feel much more productive in my computer programming, maybe 3 times more productive. And now I write in languages that other living people can still understand, like Python. Also, much more intelligent. I actually feel smarter. And I think anybody who's playing with AI can become smarter. So I think we can really look forward to a world where everyone will be smarter. Not just smart students, not just technologists, but everybody. And this, I think, is an amazing opportunity for mankind, because intelligence has been selected. We became more and more intelligent with the evolution of human beings. And this will continue. Now, some people are worried. They're saying AI is so smart, it can write the slides by itself. Who needs me? So I say that AI is very smart. human beings are very smart, but together they are smarter. So always human beings and AI, men and women and AI, will be smarter than AI by itself. Maybe AI will do things that we don't want to do. There are many things now that we don't do through smartphones. I also think that the smartphone will be our introduction into AI. ChatGPT on the smartphone is very good at listening to voices. So it listened to your speech, and it understood all the English, and it said it was a very good speech. I can show you. So it does this to me. I give a speech, and it listens, and it says, you forgot this point, you did this. It's very helpful. It's not giving the speech, but it's helping me be better. So I think this is an amazing time. You need to learn two things. One is to ask questions, and we will see in the question time lots of good questions. And the other is to be able to understand fake from real, to be discriminators. If somebody says that this television weighs 1,000 kilo, you probably ask, is it made from gold? No. Even if it's made from gold, it doesn't weigh 1,000 kilos. So common sense, the kind of general common sense you get from physics, is very important. I have found that the AI models are very bad at arithmetic. Sometimes you say 1 + 2 + 3, and it says 5. And that's fine. Somebody said to me, I shouldn't be worried, because it's a large language model. It's not a large science model. It's not a large mathematics model. But these models are coming. We will now have specialized models. In some ways, the AI now is like an intelligent generalist. It can become a specialist. And that's easy to do. It's very easy to make extra training in vocabularies and so on. So I think we look forward to a future where in a couple of years' time, our phones will translate any language in real time to what we're listening to. This is now a reality. If you can understand the text, you can make the translation. And to convert text to speech is easy. The hard thing is understanding different accents, different people. And it's amazing. When the young lady was announcing the music, I got an English translation for myself immediately. I think we can look forward to a world where information is at our fingertips. But we need to think what we can do that is better than that. And this is the important thing. AI is a tool for making us better. And I think this is really exciting and really important. Thank you. Thank you. It's great. Thank you. I like very much. Thank you.
멋진 강연 감사합니다. 이제 Q&A 시간입니다. 강연 내용 아니면 기타 궁금한 사항이 있는 친구들은 손을 들어 질문해 주시기 바랍니다. We'll have a Q&A session. And if you have any questions, please raise your hand.
This lady. I like questions from girls more than questions from boys. So, because girls are usually not asking questions.
Hello, I'd like to question about, can biology help understand AI? I mean, can AI that had reached a certain level can be analyzed by classic methods of science?
I think I need you to repeat the question because my hearing is not great and I left my
sorry.
phone there. It's okay, I'm kidding. Just
Okay.
say it more clearly so I understand.
What I want to ask is, can classical methods of scientific field can help the understanding of new technologies like AI?
So you're asking whether biochemistry experimentation it can help? Can anyone help me with this? Oh, biology can definitely help AI.
Yeah.
I think that biology already has helped AI.
Yes.
in the basic design. I think we will see in the next 100 years biology changing AI, AI changing biology, and so on. There will be a dialogue between them. And, people ask me about difficult problems in the future. And I say we need to wait and become smarter. I think, a lot of people worry about that we won't need to do experiments. But we will need to do experiments. Experiments may be done in special laboratories that are controlled by robots. But people will always be important. I think people have an amazing ability to learn new things. If you look at a 3-year-old child with a smartphone, he really knows it very well. And it's something completely unnatural. When you give a child nowadays a book, he hits the corner to turn the page. He doesn't understand that you turn the page. So I think we're very adaptable. Human beings are very adaptable. But also I think that it's not just one human being, it's many human beings. And we're different. I think that maybe they need to learn from biology to make the different AIs different from each other. So one thing I read about GPT is that GPT is actually 16 different models. And the models have been trained differently. And when you ask a question, all the models answer, and then they choose the average or the consensus of the answers. That's a good idea. I would say that's almost an idea from biology. But it's not just AI that needs to learn. I mean, the world is not just AI. We need to have new materials, new ways of converting energy, new ways of transportation. Nothing we can make today is as good as skin. Plastic is terrible compared to skin. So we need to learn from biology. And I think we're in a good position because 100 years ago, we couldn't learn from biology because we didn't understand biology. And now we're understanding more and more from biology. Chemistry, there's a new kind of chemistry called click chemistry. Got a Nobel Prize just last year. And click chemistry is the biological way of doing chemistry. So I think we should never forget biological intelligence. But I think also AI can affect biology. So I think like in that triangle, there are many connections. And I think we will be doing experiments. I think it's very important to be very broad, to have an education like you get here that is art and music and everything else. Life is an amazing thing, and it's not just science. It's also nice to walk in the street, to see the sky, to look at a tree. There's so much beauty around us. And that's very important because when you work, you become very focused on your work. You need something to relax you, to open you. So I think this is a great time.
Thank you for an answer.
다음 질문할 학생 있나요? 여기.
And maybe you'll stand up when you answer the question for me, okay? It's fine. Ask the question.
Hello, Professor Levitt. My name is Hyunjun, and I would appreciate it if you could call me Ethan. Prior to the question, thank you for your impressive lectures on the relationships between humans, biology, and computer. So the question is, recently the artificial intelligence that creates pharmaceutically effective molecular is now getting attention. I think it does not seem to make that practical one yet, but do you think those AI could make the effective molecular structures for actually work in the human body in the foreseeable future?
So I think that's a great question because human health and human well-being is something that we're all concerned about. We don't necessarily want to live 200 years, but we would like to live in a healthy way. And biomedicine and health practices are very, very important. So AI is in fact being used to help drugs. One of the problems with the current pharmaceutical industry is that it takes about 10 years to design a new drug. and it costs about $1 billion, and it has a success rate of 10%. So that's really scary. And AI has been shown, there are two companies, one Exscientia in Britain, another country is actually called In Silico Medicine, and I'm actually a consultant of that company since 2014, and they're trying to use AI to make drug design more quick. And they're doing it, drug design is like a long tunnel. You start with a disease, you think of a molecule, you think about safety, and each time if you make a mistake, you have to go back to the beginning. You can't go round. If the drug is poisonous, you can't say, oh, how do I make it unpoisonous? So it's a long pathway, and for AI to be effective, you want to shorten the 10 years, maybe to 18 months or 1 year, and you want to reduce the price from $1 billion to maybe $100 million, and maybe the success rate the same. So AI is very good at each of these steps. And I was just at a meeting before I came to Seoul, at a meeting in Beijing, that was discussing AI for healthcare, for medicine. And this is very new and very important. I think it will have a huge effect because we will get new and better drugs. And we need new and better drugs. The drugs, right now, it is so expensive that the big pharmaceutical companies only want a drug that has a big market. They don't want to make a drug that can help 1 million people, because that's a small number. So I think we're going to have a big revolution in that area. I think that's a very important area. I would say that there's another way AI can help keep us healthy. And that is, AI is in our phone. And the phone knows when you're eating, knows when you're washing your hands, knows when you're sleeping, knows when you're exercising, and the AI can give you advice on being healthier. At your age, you don't think about this, but when you get older, even age 18 or 20, it's very important to balance exercise and food and rest, very important. And the AI can be very helpful because we are so attached to our phones that the phone can make you do anything. If the phone says, you did not sleep enough last night, until you sleep, no TikTok, no internet. You would do anything. You would go crazy. Or the phone says to you, you didn't go to the gym today, no movie. So I think it's a very powerful device, and I think we will see this, maybe not as punishment, but I think we can track human health in a way that is good for all of us. Already, the smart watches are doing this. So my Apple Watch, when I wash my hands, it makes me wash my hands for 20 seconds. If I stop before, it's not happy. If I get to 20 seconds, it rings a bell and says, well done. So this is stupid, but I always wash my hands enough for 20 seconds. I used to wash my hands, like this, very quickly. So it changes behavior in a healthy way. So I think we're going to see dramatic influences. I think we all carry with us a very powerful computer already. So AI through the smartphone, we have the internet, 5G, 6G, faster and faster. We will be able to do amazing things. And there's a very big diversity of companies who are working on this in many countries. At the meeting we had yesterday, there was a couple of wonderful talks from senior Korean executives, and I forget the name of the companies, but very high-level companies, just talking about how you have to spend your whole life learning, and so on. So I think, you're really living in an amazing time.
Thank you for your answer.
자, 다음 질문하고 싶으신 분?
You choose. Maybe you do once this side, once that side. So someone from this side, maybe.
Thank you for your presentation. You emphasize the importance of cooperation between computer and human to make a synergy effect. And yes, there are a bright future that computer and human can cooperate to make a great result, but there are also a dark future that artificial intelligence will replace the artists, songwriters, and even scientists, that human will gonna do a work that even artificial intelligence deserted. So I wonder your take on the dark future of cooperation between AI and HI.
So I think, again, a very important question. Immediately, we're worried about AI replacing many of the things we do. But, you know, a good artist using AI will be better than AI by itself. And a good writer using AI will be better than himself. And the same thing is true for a scientist. So I think the combination, not only that, but we will become smarter as we use AI. And I think we will become smarter quite quickly. So that isn't what worries me. What worries me more is armies of drones, you know, robots fighting wars, and so on. And this is a much more great danger. It's interesting to look at other great discoveries. And well before my lifetime, it's a discovery of printing. In Europe, in the, I guess, 16th century with Gutenberg. In China, much before. Now, in Europe, printing had a terrible effect. There were many, many deaths and fights between religions and all sorts of terrible things. And then it settled down, and we had the Renaissance, we had the blossoming of the scientific age. I mean, all the science came from that. So it's hard to say. In China, when printing was developed, it was quite a peaceful time and very strong control. So bad things didn't happen. But we also didn't get the great blossoming of culture that happened in Europe. So I think, you know, I think we have to believe that human beings are not crazy, and that we have to realize that force is not a way to go ahead. You know, one of the things that makes me optimistic is that AI should also make governments more smart. It's very, very difficult to be a government. To be a prime minister is 1,000 times more difficult than being a scientist, because they have to deal with so many different things, and they have to balance the different things. They can't say all the money goes to students, or no money goes to students. They have to get the right number, and it's very, very hard. And I think that AI can help very much in this, because AI is very good for taking lots of information from many different reasons and working on it. So I think this is going to happen. And, you know, if everyone in Seoul can go to an AI machine and it would tell us how you fix the traffic problem in Seoul, then the government knows that everyone knows this. It's not hidden. They have to do something about it. So I think it'll be much more difficult to fool the people. And unfortunately, governments sometimes like to fool the people because they like the power and they want to be re-elected. And by fooling the people, so it'll be harder to fool the people, and that will lead to better government. So I think we have to be optimistic. But I'm not worried about people being replaced. I think, you know, if you think about smartphones, so some people refuse to use smartphones, and they suffer. They suffer so much. Even grandparents who use smartphones can have a conversation with the grandchild. The grandchild can make a painting and send to the grandparent. Now, if the grandparent says, oh, I'm too old to use a smartphone, they lose. So I think we have to be optimistic. You know, many bad things could happen. In 1 week, a big meteorite could hit the Earth and we would all be extinct. This could happen. Maybe 1 month, we don't see it now, but it could happen. There could be a big storm on the sun and all the electronics on Earth would be destroyed. So, you know, but if you look back over evolution, there have been many, many bad things. If we look back over human evolution of about 2 million years, there has been global warming and ice ages, global warming and ice ages, and yet things keep on getting better. If we look back over the last 300 years, since we started to have advances in technology and so on, there were terrible things. There was nuclear weapons, there was world wars, there was invasions, there was cruelty that you cannot imagine. But human beings today are much, much better off than they were 300 years ago. more education, more food, more children living, more connected. So I think it's good to be optimistic.
Thank you for your idea.